Okay, hello MCR3U. This is Mr. Boudreau, your substitute teacher for Monday's class. I'm making this video because I was supposed to be your substitute teacher anyway, so Ms. G asked me to cover sinusoidal functions and graphing sinusoidal functions with you. Here I am in my house. By the way, the fish tank is fine. There's the fish tank. You guys can rest assured that the fish are being well taken care of while we are under quarantine. Let's have a look at what we're doing today. We are reviewing the features of sinusoidal functions, so that's something that we did on Friday with our water wheel investigation. We're going to examine some key points of the parent sine and cosine functions, also something we mentioned during the water wheel investigation from Friday, and that's the old stuff, so that's all review. I'm doing that because it's March break and I figure you guys probably forgot it. Also, there were kind of other things to think about during Friday, so maybe it didn't really land so well. Then we're going to get into new stuff. So determining the equation of a sinusoidal function from its graph using transformations of, hey, those key points that we learned about on Friday. And then we're going to graph a sinusoidal function using what we've learned about its transformations. And then the last piece is putting it all together and actually using these equations of sinusoidal functions without graphing it, just the equation, to determine properties of its motion, or potentially getting the equation from a graph, then using the equation to find other properties of motion, things like that. So that'll be the putting it all together. So I'm going to put those away, but what I'm going to keep on the screen at all times is the current topic that's going to be down here all the time. Also, there's going to be timestamps under the video, so you'll be able to jump around to different current topics. And I'm also going to keep up on top a little keep in mind, because we want to be able to talk about what these different functions are and what they mean. And as I'm blabbing on about something or writing on the whiteboard, it's good to remember why I'm doing it. So let's go to our note. Here I am down in the corner. Here's the note. We're going to start with this. We're going to start with this as our review. This was a question at the end of Friday's note, which asks, determine whether the graph represents a periodic function. So you have to remember what a periodic function means. And then if it does, so we'll do this after we determine if they're periodic functions, we have to determine whether it represents a sinusoidal function. So, periodic function, let's take a minute to think about them. Let's examine these four functions and we'll see, we'll think about it. And I think it's pretty obvious which one is not periodic, and that's this guy here. So that guy, not periodic. Reason being, if you examine it, it just keeps going up. Just keeps going up and up and up. There's no indication that's going to come back down. And the point of a periodic function, or the definition of a periodic function, is that it comes back to the same y value over and over in x. There's like a kind of a periodic maybe thing to it, but that's not enough to classify the whole function as periodic. It just has a little bit of periodic character, but that doesn't mean that the whole function is periodic. The other ones here, this one goes up, down, always hits the same y, always hits the same y down here. So yeah, that one's periodic, that's good. This one here also hits the same y, hits the same y, hits the same y, periodic. And this one here is also very obviously periodic, same y, same basic pattern, same basic shape. So pretty easy to tell when something's periodic. Green is periodic. They're all periodic. Now within these periodic functions, we have to figure out whether they're sinusoidal or not. And looking at them, this one, clearly not sinusoidal because you don't get that nice swoop, that flat area, that smooth curve that you get in a normal sine wave, so that's not sinusoidal. This one, also not sinusoidal. You do get those curves, but it's not a single wave going across. So only this one, I'm going to change the color on that, only this one is sinusoidal. Only that one is sinusoidal. This one looks like it might be two sinusoidal functions kind of stacked on top of each other, and it's a combined function of two sinusoidal functions. But that doesn't mean that the function itself is sinusoidal. We can't really say that it's sinusoidal. Okay, so that's a review of what periodic means and what sinusoidal means. Periodic means it hits the same y over and over again. Sinusoidal is this specific shape where it's one smooth curve, and it just hits a maximum, hits a minimum, hits a maximum, hits a minimum, and it just smoothly alternates between maximum and minimum. That's the classic sinusoidal function. Please note, as it says up top, sine and cosine functions are both sinusoidal. So whether this is sine or cosine, it doesn't matter. It could have just been shifted horizontally, and we wouldn't even know if someone started with a sine or a cosine here. That's why they're both called sinusoidal. Okay, so that's that one. Let's review how we got there. The way we got there was by doing this water wheel activity. You guys had this water wheel. You had a little mark on it, and we started with the mark in standard position here on the right, and we rotated it counterclockwise, and so it went up, and then all the way left, and then all the way down, and then all the way back as we rotated it through. We went 30 degrees at a time, and we measured what we got, and most people got something like this, or something close to it. Some people got, like, for example, 0.49 instead of 0.5, but the pattern is what we were interested in. Probably the most important thing for the pattern, and the thing that's going to give us our key points, is that it starts in the vertical. It starts at 0, because if I'm all the way over here in my standard position for an angle, that is 0 height. You know, if this is 0 height, that's at 0 height. And then as it goes up, this is full height, so that's why at 90 degrees we've got it at 1 full height. And then it continues on to 180, where it's back to 0 height. So 180 back to 0 height. Then 270, as it continues on down, we're at minus 1 because we're below. And then back to 0 height, and then I'll just repeat over and over and over again. Horizontally, right? Horizontally, if we're talking about horizontally, which means now we're thinking about horizontal. When we're at standard position, we're actually starting at 1. We're starting at 1. We're starting furthest away from standard position. Then we go to 0. We go to minus 1. Then we go back to 0 when we're at 270, and then we're going back to 1. So when we look in the horizontal, we get 1, 0, minus 1, back to 0, back to 1. And that's what we saw in our investigation. You know, you should have this whole table filled out because we finished that whole table. Then we checked with our calculator, we checked sine theta and cosine theta, and surprise, surprise, the sine matched the vertical displacement and the cosine matched the horizontal displacement. And that's what you should have noticed. And then we were asked to do a thing on Desmos. So let's go over to Desmos, and we plotted sine theta and cosine theta. Let's just go with sine theta here. Remember that sine theta matched our vertical displacement, because when we're over here, we are at 0. We're at 0 height. We move up here. We're at full height. We move down here. We're back at 0 height. We move down here. We're at negative the full height, and then we move back to 0, and then it just repeats that cycle again. But this doesn't seem right? It does one full repetition every 6.28. That doesn't seem right. The reason for that is that we're in radians, so we're going to go over to degrees, and now we get this incredibly long periodic function, because it takes 360 degrees for it to go up and down by 1. So what we're going to do is, I'm just going to fix this up and go as suggested from minus 30 to 400, and then the y-axis, we'll make that a little bit nicer too, from minus 2 to 2, and now we have that nice sine wave. So once again, we start in standard position at 0 degrees, we move up to 90 degrees, and at 90 degrees, which is right there, we are at full height. Then at 180 degrees, we're back to 0 height, because we're just interested in the height level. Then we move down to 270, which is our low, our minus 1, and we move back up to our starting position, which is at 0 height, and that's 360. So that's sine x. If we look at cosine, which is our horizontal, the same thing when we're in the horizontal. Now we're all the way over to the right, which is +1. At 90 degrees, we have moved up there, right? We've moved up there. That's in the middle. So we are at 0 horizontal distance. Then we're all the way over to the left, and the left is negative in normal Cartesian plots. So that's -1, that's down here. Then we move to, from there we move down to 270, which means we're back in the middle horizontally, so we are back at 0. And then we finish back at our starting point, which was all the way over to the left, which means that we are full distance away. That's our review of sinusoidal functions. So sin x and cosine x are very similar, and like I said before, they're just horizontally shifted. So if I do something like this, x plus a, or 90, right? You can see that if I move x plus 90, it actually perfectly matches the cosine. If I move it by like 80, you'll see it's a little bit off. If I move it x plus 90, it'll be dead on. So that's our review of sinusoidal functions, which means that our first thing, review features of sinusoidal functions, is done. Which means we're now going to move on to the key points of the parent sine and cosine functions. Moving on to the next step, key points of sine and cosine functions. So, key points and cosine functions. Right, and keep in mind, here, what I'd like you guys to realize is as we were moving along in our circle, it was always 90 degrees, 90 degrees, 90 degrees. So one thing to keep in mind is that the key points are equally spaced on the x-axis. Right, key points are equally spaced on the x-axis because it's 0, 90, 180, 270, 360, 450, 540, 630, and 720. So always 90 degrees apart. But if we have a horizontal compression, they're still going to be equally spaced, which is very important. Okay, let's move over to the document camera. And in the document camera, I've got one of Miss G's whiteboards, so I just stole one of our whiteboards. I've got it here on the table, and I've got a camera pointing down, and what we're interested here is key points. So let's draw a typical sine wave and a typical cosine wave. All right, sine x and cosine x. So here's sine x, here's cos x. Let's actually match the colors that are on that Desmos graph that I've got. So I believe sine x is in red, so sine x, and cosine x is in green. So sine x starts at 0 because it's the vertical on our wheel, and it starts at 0 when it's vertical and then moves on from there. It starts at 0, moves up. It does one of those. And this is one repeat. That's one period. Cosine x, because it's the horizontal, and we're starting all the way over, it starts all the way at the top. And there's only one way to go. When we're starting at the top, we have to move down. And then it continues on like that. So that's cosine x. And our critical points, or our key points are here 0, 0, here 0, 1, where we start. We're going to finish on both of these at 360 because in a typical circle, 360 is our period, and it's back at the same place, back to 0. Ooh, that's not 360. Oops, sorry. Brain fart. That's 360. And it's back at 1. So at 360, it comes back to the same place. At 360, it comes back to the same place. Right between those two, you're at the opposite side. So here at 180, this guy's at -1. Here at 180, it's on the opposite side, but it started at 0 height, and then it's coming back to 0 height. So at 180, this guy's still at 0. And then remember the keep in mind up there, the keep in mind, it's equally spaced on the x-axis. So this guy here and this guy here, this is 90. This guy's 270. This one's at 0, this one's at 0. This one up here, equally spaced 90, equally spaced 270. 270, that's at -1, and this is 90. And that's at 1. If you're ever worried about it and trying to remember, just do that the wheel thing in your head again, and it's pretty easy to get this right back. Yeah, so those are the key points. The key points are equally spaced on the x-axis, and they're spaced equally, top and bottom. All right, so those are the key points. We have reviewed the key points of sine x and cos x. So back to the front cam, and let's go back to this. We have reviewed the features of sinusoidal functions. We've examined these key points and linked it to the circle, making a circle, and thinking about whether vertical or horizontal is what we're interested in. Now we're going to get into the actual note. In the actual note, we are going to go back to here. So I'm going to take this away. We're going to change our current topic to interpreting a graph of a sinusoidal function. Yeah, a graph of a sinusoidal function. And then keep in mind, we can choose sine or cosine as a parent function. So that's something that we're going to get into in a second, is that we can actually choose sine or cosine as a parent function. It'll be one of the first questions I ask you about this activity. So we're going to close that. I don't want to save changes. We're going to open this guy. Let's open that up and move over here. Okay, great. Here is the challenge that we are faced with in this note, and that is to determine the equation of the sinusoidal function from its graph. And it says there's a nail on the circumference of a water wheel, just like the water wheel that we had before. It's moving as the current pushes on it, and it can be modeled by the graph shown. So here's the water wheel, and here's the nail. We see that it starts at the top of the water wheel, the height. It starts at the top, and it moves. All this graph tells us is height versus time. So all we know really about this thing is that it's going up and down. It's going up and down and up and down and up and down. It's kind of interesting to note that we don't know whether this thing is going clockwise or counterclockwise, because if it goes clockwise, I'll have my finger here. If it goes clockwise, it's going up and down. If it goes counterclockwise, it's still just going up and down. So we can't actually tell which direction it's spinning. All we know is that it's going up and down, up and down, up and down. And we get this sinusoidal type trace because it's a circular motion. So how can we determine the equation of a sinusoidal function from its graph? Well, the first question I'm going to ask you, like I said I would, is what makes more sense to graph this function? Does sine or cosine make more sense? And we're going to jump back over to the camera view, look at that function, and look at our two functions here with their critical points, with their key points, and tell me which one makes more sense to transform in order to get this function plotted. You know, take a minute to think about it. Maybe pause the video, wait until you have an answer, and restart the video. I'm not going to just have dead air happening, so I'm just going to give the answer in 5, 4, 3, 2, 1. Okay, the answer here, the easier one to use to plot this specific function, we have to look at where it starts. So if we look at where it starts at its peak. It starts at the top. And then we compare that to these functions. Which one starts at its peak? It's cosine x, because it starts at the peak. The reason that this is important is that when we stretch it or compress it horizontally, the x-axis is completely unaffected, so the y-axis is completely unaffected. Right? So that's going to stay exactly there if we stretch and compress horizontally. So this is a useful one. Excuse me, a useful one to use when we're starting it. So we're gonna call this a cosine function. We're gonna transform a cosine function to get the job done. Okay, the next step is to go back to our function and identify these critical points. Let's go back over here and let's identify these critical points. So we've learned about a few different things to it. One thing we've learned about is the axis. So when we find the axis, what we want to do is we find the maximum and we find the minimum, and the axis is going to be right between the two. You can do this with an equation. It's just max minus min divided by 2. Sorry, my mistake. Max plus min divided by 2. Max plus min divided by 2, the average between the two, and that would give you 1, or you can just kind of eyeball it here because it goes from 3 to minus 1. Right between them is 1. So there's the axis, the equation of the axis, y equals 1. Let me actually write that in green. Axis is y equals 1. The axis is y equals 1. The other thing that we learned about was amplitude. Amplitude is from the axis to the highest point or the lowest point, or another way to think about it is it's the difference. It's half of the max to min height. That's the max minus min divided by 2. The axis, I'm going to draw here the axis in purple. The axis is from this line, from this axis line, up. The amplitude is going to be that height. So it goes from 1 to 3 and from 1 to minus 2. That means that the amplitude here is 2. Let's change that to that purple I was using, and amplitude equals 2. Amplitude equals 2 on this function. And we can identify those same, now that we have the amplitude and the axis, we can identify the same key points that we saw on the parent functions. So just to review the key points, we have, it starts at a max, it goes to the axis, it goes to a min, goes back to the axis, goes back to a max. Back here, we have the same thing. It starts at a max, goes to the axis, goes to a minimum, goes to the axis, goes back to a max. So in this case, then the key points are, let's change the text color here. The key points, I think in red, are 0, 3, 0, 3 up here. That's the max. Here we're at, and we look at this is 10, and there's 4 divisions, so that'll be 2.5, and it's at 1. 2.51. Wow, that's really big. I'm going to reduce that text. 2.51 here. 2.51 because it's hitting the axis there. And reduce that text to too small. 0, 3, 2.51. This one down here is where I reduce that size to. Down here we're at 5 and -1. -1. 1. 5, -1. We're back at 1, but now we're at 7.5, 7.51. And at the back of the top, we're back at 3, but now we're at 10, 3. 10, 3. So those are the key points that we've identified on this guy. 10, 3, 0, 3, 2.51, 5.1, and 7.51. And because that looks kind of confusing, I'm actually going to draw those points in with a little red pen. So there's the first one up here. The second one is where it crosses the axis. The third one is the minimum. Fourth one is back where it crosses the axis, and the fifth one is right at the top. So those are our key points. Let's think about what kind of transformations had to happen to this function to make that function. So we are using cosine x as our base function, and let's think about our transformations that would have had to happen to this thing. So think about them for a second. What can we tell about transformations? Let's think in the vertical first. I think thinking in the vertical first makes more sense. Has it been stretched? Has it been moved? What does that do to this function? So yeah, just think about that for a little bit, and then we'll resume in 5, 4, 3, 2, 1, and we're going back, and we're going to do the vertical transformations. So vertical transformations on this function. Boop, boop. What do we see on our function? Well, we have a different axis than the standard cosine x. Our axis mentioned up there is y equals 1. That's our axis for the function that we're interested in. And in terms of amplitude, we have an amplitude of 2, right? 2. We have an amplitude of 2. Amplitude of 2, which means that this goes to, up here it goes to 3. Here is 1. Here is -1, and that's what our function is going between. So thinking about these transformations, what we have is we've moved the axis, which means we had to move this entire cosine x up, and we moved it up by 1. So let's start with our base function here, y f of x equals cosine x. Cosine x. And in order to move it up to y equals 1, in order to take this and move it up so that the axis is no longer at 0, it's up to y equals 1, we have to do a vertical translation of it, vertical translation by 1. And that is going to come on the end. Right? It's going to be on the end of our function. It's that value there. So that's going to make every y value kick up by 1, and doesn't affect the shape of the function at all. So it keeps the same period, it keeps the same amplitude, it keeps the same phase shift. All it's done is moved upwards by 1. So that's the +1 there. And the other thing that's happened is we actually have an amplitude of 2 instead of an amplitude of 1. And that amplitude means we've had to do a stretch. We've had to stretch. So that instead of 1 on each side of the axis, it's 2 on each side of the axis. I think for obvious reasons, you can tell that that's going to be a 2. 2 cosine x plus 1. We have stretched it vertically by 2. Which means now we have a function that looks, like the correct function. It's not a great cosine. It really shouldn't be straight down there. It should be more of an angle. But I'm going to keep it because it's hard to erase it now that I've got so many colors on there. All right, so and that's the key points. Our key points In the y, we're good. We have 3, something 3. We have something 1. We have something -1. We have something 1. And we have something 3. Okay. Right, so we've done all of our verticals. Our verticals are good. We have to think about horizontal now. What do we do for our horizontals? Well, looking at this and this, it's the same basic shape. The difference is that this one goes across 360 degrees, but this one, if we go back to our thing here, this one only goes to 10. 10 is the repeat, right? At 10, it starts repeating to 20, to 30. So if we go back to our document camera, this guy here is 10. This guy here is still 0. And if we keep in mind what I've been asking you guys to keep in mind, the key points are equally spaced on the x-axis. That means that this must be 5. This is 7.5, and this is 2.5. So we have to figure out how to make sure the x values are the same or match those key points. So normally it's 360, this time around it's 10, and when we shrink it, everything else is going to shrink to match. So easiest way to do this is just to think about your period. Your period here is 360. Your period here is 10. Let's write that down. Period 360. This period is 10. Therefore, compress by 36. We have to compress by a factor of 36. Right? Compress horizontal compression by a factor of 36. So take a minute to remember where horizontal compression goes in our function. And hopefully you've remembered that horizontal compression goes inside the brackets. We're multiplying x by whatever our horizontal compression is. So in this case, 36x. 2 cos 36x plus 1 should give us the correct function. Let's try it out. Go back to here. Let's try it out. Let's try changing our Desmos graph here to be cos x. We're going to go with cos x, and we're going to apply the same transformations that we did in the same order. So first things first is we moved the axis. There, we moved the axis. We've kept the same shape. Actually, you know what? Let's actually do it in stages. F of x equals cos x plus 1. Oh, cos x plus 1. Yeah, there we go. So the first transformation that we applied, we moved it up. Then from there, we had to expand it. So expanding it, cos x plus 1, we said 2 cos x plus 1, which made it taller. Right, now it's going from 3 to -1, which is what we want. From 3 to -1. And then the last thing we needed to do was that horizontal compression. So the last thing we did was f of x equals 2 cos 36x plus 1. You see that compressing it has just made it way more compressed. But it still starts at a maximum, which is nice. Still starts at that maximum. So let's take that away and we'll change to a more reasonable x-axis. So let's say we go from -5 to 30. And we see basically the same formula that, or basically the same equation that we saw here, right? Maximum to minimum to maximum, and it takes 10 each time to do this way. So, to review our transformations, we started with our parent function, f of x equals cos x. We moved it up by 1. Then we expanded it to match the correct. So first we matched the axis. Then we expanded it to match the correct amplitude, and then changed it to be the right horizontal compression. Yeah, so that was, generally speaking, how we do it. Back to here, right? That's what we figured out. We had to move our axis up. We had to expand. Right? We had to expand, vertically expand, and we had to horizontally compress. Horizontally compress. Yeah. So that's figuring out the equation of a graph from its equation of a sinusoidal function from its graph using transformations. Remember the key point, we got to choose sine or cosine. Choose sine or cosine. Choose whichever one makes the most sense to you. And typically the way that works is you want to see what the behavior is right on that y-axis. So right on the y-axis, if I look here, right on the y-axis, this one's at a maximum. If this were sine theta at the axis, it's at the y-axis, it's at the actual axis of the equation too. If it's at the axis moving up, you've got sine theta. If it's at the axis moving down, you can flip it and have negative sine theta. Same thing for cos theta. If it's a maximum at the axis, you've got cos theta. If you've got a minimum at the axis, it's just a flipped version of cos theta. So you've kind of got four different options for sine, cos, negative sine, and negative cos, and most of the time that'll match whatever function you're trying to make an equation for. Okay, moving back, get the goals back up here. Yes, we have determined the equation of a sinusoidal function from its graph, and we've used transformations to do it. And our graph here, let's just write down what we finally decided on. The graph that we decided on was f of x is equal to 2 cos 36x plus 1. 2 cos 36x plus 1. The 2 was the amplitude, so let's change that to purple. The 36x was the horizontal compression, and the plus 1 was where the axis was sitting. And the rest of it should be black, so let me just change that back to black. Back to black. To black. So there we go. So the 2 was the amplitude, the plus 1 was the equation of the axis, and the 36 was us compressing it. Yeah, and there we go. I was just doing that without looking at it. So yeah, there's our equation, right? The 2 was the amplitude, the 36 was the horizontal compression to make sure that it matched the 10 instead of being 360, and then the plus 1 was our axis. We moved it up by 1 by moving the axis. Okay, that's good. So that learning goal is done. Determine the equation of a sinusoidal function from its graph using transformations. Next up is going to be graphing a sinusoidal function using key points. Right, graphing a sinusoidal function using key points. And our keep in mind here, we're going to keep the key points are equally spaced on the x-axis, but we're going to get rid of the other things. So key points are equally spaced on the x-axis. X-axis, key points, y values of key points. Key points represent max, min, and axis. Right, they represent the max, min, and the axis of the function. Okay, so going back to this view, take this away. We're going to copy that. And here's our original function. Here's our original function, f of x equals 2 cos 36x plus 1. If the speed of the current increases as the water wheel spins twice as fast, what would be the equation of the resulting function? So when we think about that, we go, okay, well, twice as fast equals half the period. Right, it's twice the frequency. It means it'll come back around and it'll do one full loop in half the time. What that will do is a horizontal compression by factor 2. Which means what we're going to want to change is this 36x, right? The horizontal compression by factor 2. The horizontal compression is this 36. We're going to need to double it. So we're going to double it to 72, and that should give us the correct 72x, and that should give us the correct formula. The next question is graph the function using transformations. So what we're going to do there is actually use our key points again and do that from there. So key points for cosine. Right, key points for our cosine are at 0 degrees, the cosine value, because it starts all the way over here, is 1. At 90 degrees, it's 0. I'm going to put a bit more space between these. 90, it's 0. At 180, it's -1. At 270, it's back to 0. And at 360, is back to being 1. So those are our key points. Then we're going to go through it in order, in transformation order. We want to do stretches and compressions before we do any kind of displacements. So let's do our vertical stretch. All right, what's the factor of vertical stretch? The vertical stretch is by factor 2. Right, vertical stretch by 2. That's the purple in our equation. Vertical stretch by 2. Right, and that's going to affect the y values. So the x values are going to stay the same. So it's going to affect the y values, and the x values are going to stay the same, like I said. 270 something. And 360 something. So 0, 1, we're going to vertical stretch by 2, which means we have to multiply the 1 by 2. So 1 times 2 is 2. 0 times 2, still 0. Minus 1 times 2, minus 2. 270 times 0 times 2 here, because it's it's the vertical is 0, and 360 so 1 times 2 is 2. So this is the vertical stretch by 2. Those are our key points. Next up, from there, we can either do the horizontal compression or the vertical displacement. I'm going to do the horizontal compression by 36. Horizontal compression by 36, and what we'll do is actually just kind of shove these over so that we can match. Ooh. There we go. Horizontal compression by 36. So that means that we are, by 72, sorry, by 72. That means that we are taking every x value and dividing it by 72. So 0 divided by 72 is still 0. 90 divided by 72 is 1.25. So let's explain how I got there. It is 90 divided by 72. So let's pull up a calculator and pull up a calculator. And what we've got is, I'll clear all that. All I did was 90 divided by 72. Right, the 90 comes from my x value. The 72 comes from my vertical compression. I'm dividing 90 by 72 equals 1.25. That's how I knew it was 1.25. Oop. 1.25, comma, and that 0 stays the same place. 1.250. Now the next piece here, right? What do we do with one? We do 180. We can do 180 divide by 72. So easy enough. We could do that. Clear that. 180 divide by 72, and we get 2.5, and we can put that in. Or you can use our keep in mind thing up here, right? Keep in mind the key points are equally spaced on the x-axis. If it's 0 and then 1.25, it's going to be 2.5. So 2.5 it keeps the same minus 2. Now 270, so 1.25, 2.5, 3.75, or once again, you can just use your calculator. If you want, you can just pull up the calculator and go and clear and go 270, 70 divide by 72, and we end up with 3.75. Get rid of that calculator again. And still 0. And then here it's 5 and 2 because 360 divided by 72 is 5. You know what, this is getting kind of confusing. What I'm going to do is I'm going to turn that purple, turn that purple, turn that purple, just to show you that that's what I've affected. Turn that purple and turn that purple. And then for the horizontal compression, we've actually divided everything by 72. So 0, that one changed, that one changed, that one changed, and that one changed. Right. 72, and then there's only one thing left to do, and that is our vertical displacement by +1. Right, and we're adding 1 to every y value. So that's 0. From 2 it goes to 3. From 1, that's still 1.25, but it's going to be from 0 it goes to 1. From 2.5 it goes from -2 rather, from -2 plus 1 is -1. The 3.75 we've got it goes from 0 to 1, and at 5 it goes from 2 plus 1 is 3, and those were all green. So let me change that color to the green that I was using. Back to the green that I was using. Green, green, green. So those are the transformations of our key points. Right. The first stage was multiplying all of these. Right, multiplying them times 2. Times 2. Second stage was taking all of these in blue, taking all of these and dividing them by 0.7, dividing them by 72. Then the third part was taking all of these values, and adding plus 1, plus 1. Now we have a new set of key values that we can use to graph our new equation. So when we graph it, right, we have that at 0 we start at 3. Okay, that's 3, 0, 3. Keeping in mind that the key points are equally spaced on the x-axis, we start at 3. We're going to go to 1. Right, at 1.25. We're going to go to -1, back to 1, and back to 3. Right, 3, 1, -1, 1, 3, and they're all equally spaced. Which means we can draw the curve now. Something like that. Just pretend I did that right. No, that should go there. We drew the curve. That is -1. Oh, sorry, that's not -1. That's just 1. This is -1. This is 1. And that's back to 3. 3, 1, -1, 1, 3. And then we have to think about the x-axis. So, on the x-axis, right, this is 0. This is 1.25. 1.25. This is 2.5. This is 3.75, and this here is 5. And that's how you sketch it out. If you want to do the proper transformations of all your key points, that would be a good way to go. Remember to do your stretches and compressions before you do any kind of displacements, or else it won't work correctly, because those are more fundamental to the function. They're nested further in. Okay, so I think that takes care of one of our goals, right, to graph a sinusoidal function from its transformations. So we've done that. And our new topic here is going to be getting information from sinusoidal functions. All right, let's get some information from sinusoidal functions. So this is kind of the application type section. You can figure out how big a circle is, how often it repeats, things like that. Right. And we're actually going to keep the same keep-in minds in mind, because those are important features of sine functions, or sinusoidal functions. Let's continue on. Here we go. A group of students is tracking a friend, John, who is riding a Ferris wheel. Oh, I should probably put that up on screen. A group of students is tracking a friend, John, who is riding a Ferris wheel. They know that John reaches the maximum height of 11 meters at 10 seconds, and then reaches the minimum height of 1 meter at 55 seconds. Having you develop the equation of a sinusoidal function that models John's height above the ground to determine his height at 78 seconds. So we're being asked to do two things here. Our goal is twofold. Number one, find the equation of this motion. Number two is determine f at 78 seconds, right? Determine the function, determine the value, the height at 78 seconds. Or I guess maybe not f, let's call it h. Determine the height at 78 seconds. So looking at it, we can already build a basic sketch of this motion. We know what it looks like. We know that at 10 seconds, John is at a maximum. And that maximum here, as mentioned here, is 11 meters. Right, maximum is is 11 meters. Now there's a minimum 1 meter, so down here is 1 meter. All right, 1 meter. Minimum 1 meter, and that happens at 55 seconds. So that happens at 55 seconds. So that's what we know about the motion of this Ferris wheel. So we know that he starts up here, he ends down here. We know it's a sinusoidal function, so it's going to have like a swoop as it comes down. We know that about the motion, which means we can infer other things about the motion. We know that before 10 seconds, he would have come kind of up. Right? He would have come up like that before the 10-second mark. And then after the 55-second mark, he's going to go back up. And so on. We're going to have a curve like that. Not exactly like that. Let's actually make that a little bit, but that's even worse. And pretend that didn't happen, and that's more like it. And it's a better sine wave. So we're gonna have a motion something like this. So the question is, what can we determine about this equation? What kind of things can we do? Well, the first thing we can do is figure out the axis. What is the axis? Where is the center of this Ferris wheel? Well, thinking about it, right, if this is -1 down here, or sorry, not -1, I keep saying -1, it's 1, it's 1 meter. If it was -1, he'd be going through the floor, which you don't want in your Ferris wheel, and this is 11 meters. Think about how you would be able to figure out where that is, where that center area is. And I think it's pretty straightforward. You can tell that this thing is 10 meters wide. So this guy here must be at 6 meters. Right, that must be 6. Because it's 5 and then 5. If you want a mathy way to do it, everybody likes having a formula for this. The axis is the max. It's the average between the max and the min. So it's the max plus min divided by 2. Divided by 2. So the axis here is 6. Right, we have an axis. At 6. And if we think back to what our basic sine and cosine function looks like, their axis is down at 1. So we already have one of our features here. So it's 11 plus 1 divided by 2, just to prove it, equals 12 over 2 equals 6. So that's your axis. We'll make it green. So axis max plus min over 2, it's 6 meters. And the axis, if you recall, that's our vertical displacement. Vertical displacement by 6. Vertical displacement. We've already got 1 out of our 4 things. The next piece is going to be amplitude. Right? How far is the amplitude? Now that we have the axis, it's relatively straightforward. From 6 to 11 is 5. Right? That's 5 meters. So our amplitude is going to be 5. If you want a mathy way to do it, everyone likes the formula, like I said before. The mathy way to do it is that the amplitude equals, that's kind of large. Well, whatever. Amplitude is the max minus the min. You're actually interested in the spread between the max and the min. Alright, max minus min, 10 meters, divide by 2. So half of the difference between the maximum and the minimum. So that's 11 minus 1 divided by 2. In this case, that's 5. And the amplitude is our vertical stretch. right? So typically vertically, it's pretty simple to figure out the vertical aspects of periodic functions, of sinusoidal functions, because you're always going to have a max and a min, and both the amplitude and the axis just depend on the max and the min. If you don't know the maximum and the minimum value, it's quite a bit more complicated to figure it out. So we've already got our vertical stretch and our vertical displacement. The next thing that we could do is figure out the, let's choose a color here. How about red? Let's figure out the horizontal displacement, or what we often call the phase shift. And in order to do that, we have to figure out, do we want to model it as a sine or cosine? Right, sine or cosine. The way to figure out if you want to model it as a sine or a cosine is to look at what you know. Do you know the max or do you know the middle? Right, because cosines start at a maximum and sines start in the middle. So if you know the middle, if you know the equation of the axis, you can use the sine. If you know the maximum and a specific point on the maximum, you can use cosine. In this case, we have a specific point, right? We have 10, 11. We have 10, 11 as a point, one of our key points. So that's a maximum, which means we probably want to use cosine because we know the max. We know the max. And it has that max at 10 seconds. So the horizontal displacement is plus 10, right? Because in a normal cosine, it would start at the max and start coming down. A normal cosine starts at the max, starts going down. This one starts at a max and starts going down, but it happens at 10 seconds. So we need to move that horizontal displacement by 10 seconds. And you can't see my screen down there, so I'm going to move my thing back here. So yeah, horizontal displacement is plus 10 because it's moved by plus 10 seconds. We're at a max here. And then the last piece is the period. Right, the period. Let's look at our period. I'm going to make that in blue. Period. Right. They haven't given us the whole sine function. They've only given us this piece in blue. We had to infer the dotted line. We only know for sure that this happened. But when we look at it, how much of the period does this represent? How much of the period does this represent? Maybe think about it for a second. 5, 4, 3, 2, 1. This is exactly half of the period because the key points are equally spaced, just as mentioned up in the corner. Ooh, not that corner. There we go. The key points are equally spaced on the x-axis. So this is, from max to min, we've got to go from min back to max. So max, min to max, that is one period. This represents half of a period. So when we want to think about that, we know that 0.5 of a period is 55 seconds. That means that a full period must be 110 seconds. Full period is 110 seconds. From there, we have to figure out our horizontal compression. Right? A normal period, the parent period is 360. Parent period is 360. If you want a bit of a better example of what I'm on about, here's the period, right? It goes from max back to max, max to max. Period is 360 because in a normal cosine wave, you've got one circle, which is 360 degrees. So how compressed is this thing? Well, the compression is going to just be compression, we should spell that right. 360 divided by 110 which is, I need to figure out what 360 divided by 110 is. Let's pull up the calculator. 360 divided by 10, divided by 110, 360 divided by 110 is 3.272727272727. I don't want to write that. I really don't. So what I'm going to do is just reduce that fraction. I'm going to take away my calculator. It's not a nice round number, but in math we can just reduce the fraction. So 360 over 110 is also the same thing as saying 36 over 11, right? Just 36 over 11, which I don't think can be reduced any further. So I'm going to keep it as 36 over 11. Okay, now we know everything. 5 is the vertical stretch. Horizontal displacement plus 10. Vertical displacement is 6. And the compression, the horizontal compression, is 36 over 10, which means that we know what to do. Let's make a base. Here's our parent function. We're starting with f of x equals cos. I keep writing cos. Keep putting an x in there. F of x equals cos x. Let's put in our modifications. The first thing that we have is the vertical stretch. That's our a value. So we have to put a 5, and that 5 should be purple because that's our vertical stretch. Vertical stretch, purple. We're going to go back to our parent function now. 5 cos. Now inside the brackets is going to go all of our horizontal stuff. So in front of x is going to be our horizontal compression. In front of everything is going to be horizontal compression. So 36 elevenths, pop. And then inside another bracket is going to be our horizontal displacement. Horizontal displacement is 10 seconds to the right, which means it's going to be x minus 10, because horizontal kind of works opposite to vertical. Close those brackets. And then the vertical displacement, to get that axis in there, is plus 6. Plus 6. You know what, I'm going to put square brackets here just so it's easier to parse this stuff. And that'll be our function. That's the function that should match this Ferris wheel. Right? We found the equation of this motion. That's the equation of this motion. It's all color-coded for you, so hopefully you can remember how that worked. So that's part 1. Part 1, done. Part 2, right, part 2, if we recall what it was, is to find, part 2 was find the height at 78 seconds. The height at 78 seconds, So to do that, we're going to take this guy, right, and sub in 78 for x, right, 78. I'll just kind of underline it. There's the 78. We're putting that in for x because it's asking us what is John's height above the ground at 78 seconds. And we're going to put that into our calculator. So continuing our tradition here, equals, I'm going to copy that, equals, I'll do that, so 78 minus 10, that's the most inside bracket, so that takes us to 68. Right, 68 equals 36 over 11 times 68. Ooh, I don't think I can do that one in my head. Let's pull up the calculator. So, 36 divided by 11 and times 68 equals 222.545454554. We're just gonna go with 222.5, I guess. I don't know what Miss G uses as your rounding, but I'm gonna go 222.5. We're gonna round to the decimal. Right, next up is taking the cosine of that value. So equals 5 times whatever cosine 222.5 is. Let's do that. Let's take its cosine, which I'm in degrees, yes, is minus 0.736. We'll say 737. Minus 0.737. Yeah, and there's still the plus 6 on that side, so those still exist, and the 5 is still there. And then the very last piece, right, we have to multiply this by 5. Equals 5 times that, so let's multiply by 5 times 5 is minus 3.68 minus 3.68 plus 6 plus 6, which we'll go back to the calculator and we'll go plus 6 equals 2.32. In this case, 2.32 meters. So we have this complicated looking question, but as soon as we have the equation, we just work through it carefully, step by step, minding our brackets, and we figure out how high off the ground John was at 78 seconds. So John was apparently 2.32 meters off the ground at 78 seconds, which, you know, I guess makes sense, because that wouldn't be, he'd be on the upswing, but not too far, because if that's 10 and that's 55, he'd only be like there, kind of at 78 seconds. So it kind of matches our sketch as well. And that's figuring out things from figuring out properties of a motion from its sinusoidal function, which is what we were interested in down here. Okay, yeah, hey, look, it's a flagpole. It goes back and forth. So this will be, you know, question 2. Let's work out what this thing is doing. And we'll do the same kind of problem solving approach. So first off, let's make a little sketch of what this flagpole is doing. It is moving back and forth from a resting position. Wow, that is a really bad set of axes. Let me try again. I'll try that a little bit better. Okay, so let's do a little thing. Back and forth from its resting position. The right is positive and the left is negative. It has a resting position. At t equals 0, the pole was momentarily at resting position. So that tells us that at t equals 0, it's in the middle. Then it started moving to the right. And then we have to look at it. We think, okay, is right positive or negative? Right is positive. So it's going to start moving to the right. To the right. Start moving to the right. It's going to get to the top. And it's going to start moving down. Right. This is 10 centimeters up here. Plus 10. And this is minus 10 down here. Right, plus 10, minus 10. Oh, let's take away my calculator. I'm going to move myself back over to the right side so that you can see a little bit better. Yeah, so it starts moving to the right. T equals 0 momentarily to its resting position. Okay, looking at this, right, we have our sketch. It starts in the middle, and that's at t equals 0, which means we can think about which one. So first, sine or cosine, first question. Always a good first question. Question number one. Number one, sine or cosine? Sine or cosine? Sine or cosine? Oh, that doesn't look great. Okay, let me bring that over here. Question one, sine or cosine? Do we want sine or cosine for our equation? In this case, I would say sine. Let's just jog our memory with a look back here. Sine starts in the middle and starts moving up. Cosine starts at the top and starts moving down. This flagpole looks just like this sine wave. It starts in the middle and it starts moving up. It starts moving into the positives. So I'm going to use a sine wave. Use a sine function. So sine is what I'm going to use. Sine. Let's use the sine wave. The reason I want to do that is that means I don't have to translate it. I don't have to horizontally displace it. Then we have to figure out the equation here. Right? Determine the equation of a sinusoidal function that describes the distance at the top of the pole is from the resting position in terms of time. So let's go through our checklist. We're going from 0 to plus 10. So, I mean, I'm not gonna bother kind of taking you through the math of it, but you can tell that the amplitude is going to be 10. The normal one has an amplitude of 1. The parent function has an amplitude of 1. This is 10 times bigger, so the amplitude is 10. The axis equals 0, so no change. There's no change on the axis. It's still 0. We don't have to change the axis. There's no phase shift. Right? It's a sine with no phase shift, so there's no horizontal translation happening here. And then the last piece is figuring out the period. Right? The period here is very, very small. It's 240 times every minute. So the period is 1/240th of a minute. 1/240th of a minute. Which is going to lead to some interesting things when we try to figure out the what the horizontal compression is, because we have to go from the parent function. So let's talk about the period. Horizontal compression. Horizontal compression, right? Our parent function has a period of 360. This thing has a period of 1/240th. It is going to be compressed down to 1 and then compressed a further 240 times. It's going to be tiny. So let's explain how that's going to work. The parent function is 360. Right? Normally it's 360. When we did it before, what we did was, if we look back at, say, this guy, right, we found the compression by taking 360 and dividing it by the period. Here the period was 110 seconds. If we go back to this one, right, it was a period of 5. So we have to divide by the period. Divided by the period. Sorry, I can't write very well. It's 360 divided by the period. In this case, it's going to get really interesting because that's going to be 360 divided by. You know what? This will work better if I do this over on the whiteboard. So let's do this over on the whiteboard. Let's explain this on the whiteboard. Do I have a fresh whiteboard? Yes, I do. Okay, so, all right, the horizontal compression is 360 divided by the period. In our case, the period is 1/240th of a minute, because it says that it wiggles back and forth 240 times every minute. You can see that right here, 240 times every minute. 240 times every minute. So the period is 1/240th of a minute. Therefore, the horizontal compression is going to be 360 divided by 1/240th. Right? 360 divided by 1/240th, which means that we have to get into some fraction rules. So take a minute to remind yourself, how do we divide by a fraction? 5, 4, 3, 2, 1. We divide by a fraction by multiplying by its reciprocal. So that would be 360 times 1 over times 240 over 1 over 1. 360 times 240 over 1, which becomes 360 times 240, which means that our horizontal compression is huge. It is 360 times 240 over 1, which I don't want to do in my head, so let's pull up the calculator again. 360 times 240. 360 times 240, which is 86,400, so 86400. Right, 86,400. It's a big horizontal compression. Like I said, it has to go from 360 down to 1, and then from 1 down to 1/240th. So it's going to be a very big number. Of course, if you have a fancy calculator, you can just do 360 divided by, and then you open a bracket, 1 divided by 240, and you close the bracket, and apparently my calculator doesn't believe in math. That's interesting. That really should work. Huh. Well, whatever. That's your answer. You have a huge compression because it's going very, very, very quickly. 86,400. So back to this view, our compression is equal to, horizontal compression is equal to 86400. 86400. Okay, so our formula then is f of x equals the amplitude first, 10, sine the compression 86400 x. There was no change to the axis, so we don't have to pull it up. Yeah, that's it. That is our entire formula there. How does the situation affect the domain and the range? So thinking about this, how does it affect the domain? Well, the domain of a sinusoidal function is that it just goes on forever. Right? No matter what you do to it, it always continues infinitely left and right. So the domain is always x is an element of R. X is an element of the real numbers, always. There's no like traditional compression, stretch, moving. Nothing about it will change that to change that in a sinusoidal function. But the y value will change. Y is an element of R, such that what happened here was we have an amplitude change. So normally it's -1 to +1. Here it is -10 is less than or equal to y is less than or equal to 10. Because it does hit 10 right at the very top. And it does hit -10 right at the very bottom. So that's solving that problem, especially this part here. Okay. This one here, the moon is always half illuminated by the sun. This is practice problem number 3. How much of the moon we see depends on where it is in its orbit. Table shows the proportion. You have some full illuminations, you have some no illuminations, sometimes where it's not illuminated, sometimes where it's fully illuminated. And then, kind of in the middle. So let's work this one out, right? First off, let's find the period. The period is going to be, a max to a max, or a min to a min, or anytime it's the same number to the same number. So I don't see any other ones that you could use for that. So let's go for a max to a max. Here, right? Here's a max. Here's another max. So the period here, 14 to 44, is 30 days. You could have also done, 29 to 59. It's still 30 days between the two minimums, right? Period is 30 days. Period equals 30. Period equals 30 days. Let's talk about the axis. The axis here, if we kind of sketch it out, you've got, it starts at a minimum, it starts at a minimum and goes like this, right? And minimum is 0, and maximum is 1, 0 and 1. So obviously the axis is going to be at 0.5. 0.5. That axis at 0.5, you can figure that out just by going max plus min divided by 2. If you don't feel like looking at it, more practically here, you can just do the formula. It never steers you wrong. So that's 1 plus 0 divided by 2, and that's 0.5, which is exactly what we figured out just looking at our sketch of this thing. So axis is 0.5. I think I have my period as blue most of the time. Period is 30 days. Axis is 0.5. Let's do the next one. So that's the amplitude. The amplitude is also 0.5. So it goes from 0 to 0.5, or from 0.5 to 1. That's going to be 0.5. But once again, we might as well just show off how we get there. Like, clearly that is 0.5, but we can also use math. We can also use, we can use algebra to get there. So we know that the amplitude is max minus min over 2. Max minus min over 2, which is equal to max minus min over 2, that's 1 minus 0 divided by 2, which is also 0.5. Hey, it's the same thing that we saw in our sketch up here. That's 0.5. 0.5. But we can get it with the algebra. And then the last thing to think about is the phase shift. So what we want to think about the phase shift is, do we want to use it as a sine or a cosine? And we always want to think about it, do we know max and min, or do we know the axis, where it hits the axis? Well, it hits the axis at 0.5, and none of these are exactly 0.5. But we do have a max, we do have a max, and we do have a min. But the classic cosine starts at the max and starts going down. So if we start it here on day 14, we can call that a cosine function from here. Right? We can call it a cosine function with a phase shift from there. So we can, if we start there, we have a phase shift of 14 to the right. We phase shifted 14 to the right. So let's add that in. Phase shift of 14 to the right. It's a cosine function. It's phase shifted plus 14. And because that's the max, and it starts going down from the max, and that's what a cosine looks like. That's what a cosine function typically looks like. So the period is 30 days. Therefore, the so a period of 30 days, the horizontal compression is equal to 360 over 30. That means the horizontal compression is whatever 360 divided by 30 is, which I'm pretty sure is 12. You know, if we wanted to bring out the calculator and figure that one out, we could, but I'm pretty sure it's 12. So now we have everything we need. We have our compression, which is 12, compression factor of 12. We have, let's see, period is equal to, you know what, let's actually make that a little bit more obvious. Equals 360 over 30, which is, 12. And it's a cosine, and it's phase shifted by plus 14 days. I should pull that over here. There we go. The cosine is phase shifted 13 days. So that gives us everything we need in order to write our function. The function is f of x. We start with cos x. I keep doing that, cos x. And then we're going to hang all of these onto it. So then our new function is, what are we doing? Well, yeah, maybe p. P for portion, p for proportion of moon visible. Proportion of the moon visible is going to be, the amplitude first, 0.5 cosine. Open that up because we have a phase shift in there. The compression, 12, x, minus 14 because that is our phase shift, and then our axis, plus 0.5. So where did these come from? This 0.5 is our amplitude because we're only going up and down by 0.5 from our thing instead of 1 like the parent function does. I keep putting the x there. The 12 comes from our period, so we'll make that blue. 12 is 360 over our period, so 360 over 30, that's 12. And as a reminder, we got that 30 because from max to max was 30 days. And from min to min was also 30 days. So we know that our period is 30. 30 days, 30 days. So that was the amplitude. This was the period. This minus 14 will phase shift it to the right by 14 because that's what we see. The first max is 14 phase shifted to the right, and then it continues on from there as a normal cosine wave. And then the plus 0.5 is the axis. Right? We've pulled it up by 0.5. You can't really have a negative proportion of the moon visible, so you've got to pull it up so that it's from 0 to 1. And that's how you solve a problem like that. So that's the third practice problem that we've done. And I think that's it. Oh, determine the domain and the range of the function. Well, let's grab our function here. Grab our function here. The domain and the range of this function. Well, like I said before, domain is just x is element of r, of the real numbers. You can't do anything that stops that from being true in a sinusoidal function. As soon as you move it, it fills in behind. As soon as you move it, it fills in on the other side. So domain is x is an element of r. X is an element of r. X is an element of r. Now for the y though, you have to figure out the minimum and the maximum. So the minimum, if you're kind of thinking about minimums and maximums, the minimum is the axis minus the amplitude, and the max is the axis plus the amplitude. And the axis is green. It's our vertical displacement. And the amplitude here is purple. It's our vertical stretch. So max and min, axis and amplitude. So here the max is 0.5, sorry, the min. The min is 0.5 minus 0.5, so that's 0, and the max is 1. So that gives us what our range is. Our range is that y is an element of the reals such that 0 is less than or equal to y, which is less than or equal to 1. So that's how we figure out the domain and the range. Domain is always x is an element of r. There's no way that because it's periodic, because it's just going to keep going and keep going and keep going forever in perpetuity. There is no end. There's no hole. There's no way not to have an x value. But y, because it's always going back and forth, back and forth, back and forth, there is a specific maximum and minimum to it. Okay, use the equation to determine the proportion of the moon that is visible on day 110. Well, we have our equation, and we're just going to go through the equation. Let's pull up the calculator. Pull up the calculator, and let's go for it. First things first, let's drop in our, I'm just gonna put some equal signs in there just to be good. Let's drop in our value for x. We need day 110. So day 110. Day 110. That means that we're going to get 110 minus 14 is 96. 96. 96. 96 times 12 . 1,152. So that's 1,152, was it? Let's just try that again. 96 times 12. 1,152, that's right. Now we want the cosine of 1,152. So cosine 0.309. So back to here. so that's 0.309 based on our calculator. We will multiply that. Ooh, clear. 0.309 times 0.5, 0.51 equals 0.1545 plus 0.5. Break that down there. There we go. I'll get that black too. Okay. And the last piece here is equals, just add that together. So add 0.5, so that'd be 0.6545. So there's our answer. That's what proportion of the moon will be covered. 65.45% of it will be covered on day 110, theoretically. Does that make sense given what we know? Well, let's see. Day 110. 30 days after 74 will be 104, and then we'll be on the downswing for 6 days, so it'll be less than 0.88. Yeah, I think that makes sense. You can always do a little self-check like that. So 0.6545 seems to make sense as an answer to me. Let's just make that a little bit better, and that a little bit better. Just show off what we've been doing. There we go, and that's how you solve that practice problem. And that's it. Hey, this homework is there, and that's there. This turned out to be quite a long video. It's like 1 hour and 40 minutes. Oh my god, almost like an actual lesson. But just a reminder, you can check the timestamps down here to jump back to each practice problem as we were solving it. And I hope it was useful for you. Yeah, thank you very much. Sorry for the awkward video. This is like the 4th one of these that I've done. I'm already feeling a little bit better about them, but maybe you'll see another one for Tuesday's lesson. Yeah, thanks. Bye.